Section 4.6 deals with relative velocity and relative acceleration. So what we're talking about here is reference frames and moving reference frames. So what we want to introduce the idea is, imagine a moving sidewalk like at an airport. We have person A on the moving sidewalk and person C on the moving sidewalk and person B standing outside the moving sidewalk, just in the hallway. And the moving sidewalk has some constant speed, we'll call it 2 meters per second, just to have a number. So person A observes person C standing still. Right, they're both on the moving sidewalk. The moving sidewalk is connected throughout and they're not moving relative to each other. So person A says they're standing still. They observe them to be moving at 0 meters per second. What does person B observe? Person B observes person C moving at 2 meters per second, right? Because the person B is just standing on the ground. So these are what we call frames of reference. And we've talked a little bit about this already. Right, and an inertial reference frame is one that is not accelerating relative to another inertial reference frame. In general here, I'm just going to say not accelerating. We can have a discussion in more detail on that at a later time. But for now, I'm just going to say it's one that's not accelerating. So let's look at some other examples. We had a moving sidewalk. We could also talk about current in a river, right? In our moving sidewalk example, the people would be walking along the sidewalk, right? So it's a one-dimensional. So let's say now that we're going to paddle a canoe across the river. Now we have a two-dimensional example. If we talk about the speed of the boat relative to the water, what will often be referred to as in still water. That's the speed of the boat relative to the water, right? So if the water were not moving, that's how fast the boat would be moving. But in the moving water, we now need to talk about how does the boat actually move. If I paddle my boat straight across, what I actually end up doing is drifting down because of the river current, right? So say I'm trying to get to this dock on the other side of the river. I have to account for the river current. So if I look at my boat going across and I want my actual path to be straight across to get to that, then I have to consider the vector sum of my velocity in still water and the current to give me my resultant or total velocity, right? The actual velocity that I get going across looks like this, and it's less than your velocity in still water because you have to fight against the current, right? Or if I don't fight against the current, what happens? So if I don't fight against the current, I have my velocity in still water, the velocity due to the current, and I end up with a total velocity like this, where I'm not paddling straight across. So these are all relative velocities, right? We're talking about still water versus the flowing water, stable ground versus the moving sidewalk. So what about relative acceleration? We've done some problems in the past that could be solved rather easily using relative acceleration. But the one thing I want to talk about here is the International Space Station and the feeling of weightlessness. Well, it turns out you are not weightless on the International Space Station. Gravity at the International Space Station is about only 10% reduced. It's something like 0.89 times the force of gravity on the surface. It might be a little less than that. It might be 0.8, 0.87. My rule of thumb there was it's about 10% is about all that I remember on that. I'd have to calculate. But if you are a person in the International Space Station, what's happening? Well, there's a force on the space station and there's a force on you due to gravity. But that means that you both experience the same acceleration because it's that force of gravity, and we know that the mass is both your inertial mass, which resists the change in motion, but it's also your gravitational mass, which determines your force of gravity, and that cancels out so that you just experience an acceleration due to gravity. So relative to your environment, there is no apparent force, right? Your environment is accelerating at the same rate you're accelerating. So in that frame, it appears that there's no force. I can't spell when I'm typing quickly. All right.